In December 1938, inside a small Berlin laboratory, the atom was split for the first time. No one heard an explosion, no flash, no smoke, only strange readings on a detector, and the quiet realization that the most stable thing in nature had just come undone. That moment marked the dawn of a new physics, the birth of nuclear fission, and with it, the proof that Einstein's simple equation, E equals mc², could transform the structure of the world itself. What began as an experiment in understanding matter would soon define an age. For centuries, atoms were thought to be indivisible, the final, uncuttable pieces of matter. Yet at the heart of every atom lies a tiny nucleus, made of protons and neutrons bound together by the strongest force known, the strong nuclear force. In light atoms, this balance holds firm, but in heavier elements like uranium-235, the push of positive charge inside the nucleus strains against that invisible glue. It's a structure waiting to collapse. When a single neutron slips into this unstable nucleus, it deforms, wobbles, and finally tears apart. Two lighter nuclei emerge, along with a few free neutrons, and an immense release of energy. That tearing is nuclear fission, and the missing mass between the original and the fragments becomes pure energy. For the first time, the equation E equals mc² stepped off the page and into physical reality. In 1905, Einstein proposed that mass and energy were interchangeable, two faces of one entity. For 3 decades, this remained a profound but untested concept. Then came Otto Hahn and Fritz Strassmann's experiments, and Lise Meitner's brilliant analysis in exile. She calculated that the energy released matched the loss of mass precisely as Einstein predicted. A few milligrams of vanished mass produced millions of times more energy than any chemical reaction ever could. The door to the atomic nucleus had been opened, and humanity could never close it again. Each fission not only released energy, but also emitted neutrons. Those neutrons could strike other uranium nuclei, causing more fissions, a chain reaction. If the conditions were right, this process could sustain itself, multiplying in a geometric surge. Control it, and you have a continuous power source. Let it run unchecked, and you unleash destruction on a scale never before imagined. This simple difference, between moderation and explosion, would define the next chapter of history. As World War II intensified, physicists realized that fission could be weaponized. The United States launched the Manhattan Project, a secret collaboration of the world's greatest minds: Fermi, Szilard, Teller, Oppenheimer. They calculated how much uranium or plutonium was needed for a sustained reaction, discovered critical mass, and designed implosion mechanisms to compress material faster than the chain reaction could escape. On July 16, 1945, the first nuclear explosion illuminated the New Mexico desert. Only a few grams of mass were converted to energy, yet the blast equaled 20,000 tons of TNT. In that instant, Einstein's equation became not just physics, but history. The bombs dropped on Hiroshima and Nagasaki ended a world war, but began a new era. Nuclear fission had shown humanity its own shadow. Yet out of destruction came a second path: controlled fission. In nuclear reactors, the same process is carefully balanced. Neutrons are slowed, reactions moderated, and the heat generated is converted into electricity. The atom that once destroyed cities now powers them. But the same principle connects them both. Mass becomes energy, bound only by how we choose to release it. Today, nuclear fission provides around 10% of the world's electricity. Its potential remains vast, carbon-free, immensely dense, capable of running for years on a few kilograms of fuel. Still, the questions it raises are as much philosophical as technical. Can a discovery born in war become a foundation for peace? Can the same physics that built the bomb sustain the planet? Meanwhile, scientists chase fusion, the process that powers the stars, seeking to unite, not divide, the atom. If fission was the key that opened Pandora's box, fusion may be the hope that closes it. From Meitner's calculations to Oppenheimer's fireball, from reactors humming quietly to the promise of the stars, nuclear fission remains one of humanity's most profound discoveries. It proved that mass and energy are not separate things. They are woven from the same cosmic fabric. To split the atom was to glimpse the unity of nature itself, and to learn that the power of understanding always comes with a cost.